panel I made for the first Maker Faire I went to, and I didn't know what to expect. And so I set up a kind of conversation piece, because this is a frame, and it just stood up there on the table that they gave us. And nobody asked about it, I would say, of the thousands of people that came past. But Leah Beakley came by, and this was at the time she'd made the fabric lily pad and was working on trying to get the connections more reliable, and talking, I think, to SparkFun about making circuit boards. So that's the era.
So I'm going to speculate about what's going on here.
Sure.
So I see a piece of copper tape that's taped to a lollipop stick, and then a piece of e-onyx, and it's sandwiched all in, I'm not sure if it's conductive tape and then shrink tubed with transparent shrink tube. What I can't tell is what the material is under. I think the shrink tube just might be fancy, shiny.
Yeah, it's a conductive heat shrink.
Ah, heat shrink with a conductive lining on the inside.
They make it inside or outside or both.
Okay, and then you have a line, like a long format pressure sensor.
Yep.
And my contacts would be the copper tape here and the resistive fabric here.
Yeah, although I'm kind of surprised that I didn't have... No, oh, you can see it. Flip it over. Look at the end there. See? Isn't there a piece of copper? You look on the very end. There's a piece of copper peeking through.
Yeah. So there's copper on both sides of the...
Oh, yeah, those are the two sides. Sorry, yeah. That piece of copper runs all the way through there.
It's cut here, but maybe it goes around the edge.
Yeah, but that's not important. What's important is the takeoff points
So
on either side.
You can't clip with the alligator clip.
Yes.
You would solder onto either side.
Yeah, now... I never imagined at that time, electrical engineers never used alligator clips for anything. They're just not a reliable connection. So the idea that people would build a lot of their prototyping life around alligator clips was not in my mind. So yeah, that's a solderable connection.
And then when you have a steel backing, you can use a magnet to... Okay, but you're not getting... It's not a slider. This is just to hold it on.
Fortunately, that one wasn't advertised as a slider. That's a straight-out pressure.
But what you have then is you have the lollipop stick. Then you have the... See, this is the conductive lined shrink tube. And that connects to some copper tape on the bottom, and then there's copper tape on the top, and then between that copper tape and the lining is the e-onyx fabric, which I'll do with a resistive zigzag. Is there a symbol for piezo resistivity? Is it the variable resistor?
Yeah, we should invent one now. It's about time that e-Textiles had its own.
I've often thought it would be cool to come up with a language for, because when you sketch like this, when you're using different materials, it'd be nice to have like, this is the gradient for something resistive, this for something conductive, and then maybe the spacing of the dots implies how conductive it is.
Yes, that's a good idea.
Yeah, then this could just be non-conductive material. Then you can have...
So the old tradition of design from blueprints, right, is a monochrome tradition. But now the tools to draw and represent things in color are just as easy to use pretty much as black and white. So what I've noticed in the hacker community is they've invented all kinds of phantasmagorical way of doing schematics, where they use color, and you might see people with a little cartoon person on the end of the arrow to illustrate somebody pressing. Why not have a cartoon person, or why not have all the interaction points in your circuit be flesh colored? So the thing is, the number of people experimenting now far exceeds the number of people going to standards committees, standardizing schematics. So,
this just reminds me, because I was playing, when I first got the sketchbook, with this idea of mixing symbols of electronics and human interaction.
Yeah, that's beautiful. There is
there
is a tradition of that in industrial design. Oh, you know those, because I see some, I think, industrial design. Well, this particular set of things is actually in the industrial design vocabulary, visual vocabulary.
No, I didn't know. This is for a friend.
Well, there are systems where you want to indicate where the operators operate things, like nuclear power control. So power control schematics have symbols associated with where the human interactions are. So that's a rich thing, and it is certainly time to start looking at that. Schematics, circuit schematics are 2D, and people have lost the connection, but almost all the symbols are flattened versions of the original object. Everything from transistors to resistors, what they would look like when they were flattened. So if you look at it, the classic one is the coil, right? The symbol for a coil, which you use for loudspeakers or whatever. It's just or inductors. The traditional one, actually, you wind them. Yeah, like that. There you go. And so I like that, because it's both what it would look like in the flat, and also to draw it just feels to me like winding.
Yeah.
So the whole thing about schematics is to lose the spatial relationships, the 3D spatial relationships, and just switch the emphasis to what the device is and how it's connected, the topology, and identifying the device. Now, the tension with e-Textiles is we don't have devices that we go buy in a store that are pre-made. We make them, and the whole joy of e-Textiles, in a way, or textiles, is that we can custom make them. We can make them go over round and curvy and moving objects. So that's, in a way, the tricky thing. Like, how would you draw a schema of
because
the lollipop stick? That it's actually important that the way I pick up the conductor over the top, that you interact with it over the top, I actually pick it up on the other side.
Yeah, but that's maybe still not important in this schematic format, but it is important in the physical implementation.
Yeah.
So there's
a loss of information.
Yeah, and if I think now about how in CAD programs like Eagle and KiCad, you can make that step really easily from, you've got the schematic, the board layout, and then you've got a 3D model of the whole circuit with all the parts as little 3D models, so that you can then go in laser cut casing that will fit perfectly on. And that's where I think then this comes in, where you want to also be able to define, if you're making your own sensors, maybe even in those softwares, to be able to build footprints, which you basically can, right? And that could be an interesting thing to do, to make a library of, even though they wouldn't be placed on the PCB board, but to be built in those softwares, so people could.
Yeah, I love that idea, and the fact that there's an opening now, because the people building those tool chains are very interested in what's going on in the DIY and hobby community. So there's a kind of opening there. At the same time, I think it's worth pushing against the specialization that produced those tools. So that comes from having an electrical engineer being different from a mechanical engineer, being different from the product engineer, and then working in teams with their own languages. And then you have this software that tries to articulate them. But a lot of challenges in completing products come about through miscommunications. So I'm always reaching for some kind of intermediate thing where I'm drawing the circuitry whilst also saying something about how the physical arrangement is. For e-textiles, it's particularly important because you have that design trade-off between complicated software that is able to get a lot of information from the textile with a small number of wires, or the other way of doing it, lots of wires, lots of cleverness in the textiles that simplifies the software. And that's a design space, and it doesn't really have a convenient language.
So it's true, before making the step into these specific programs, to just come up with these kind of conventions. Yeah,
just invent them and use the fact that we don't need a convention yet. Just to explore the space.
Yeah, it's true. I'm also hesitant to go towards let's standardize the way that we connect everything and let's come up with the conventions, because then you start to constrain the way people... I think that's what draws me to the space, and I also want to ask you now what this is.
Well,
are we too far away? But
no, I'll move on to the next one shortly, but I want to pick up because I'm reminded that every now and then I thought, I should really... I might know enough about this to write a book, or Hannah knows certainly enough to write a book. Why didn't she write a book about this? And then every time I sort of lay out chapters or whatever, I realize by the time I've written the first chapter, by the time I get to the end of the first chapter, there's about 10 times as many things got invented that haven't been written up yet. That it's too early to I wouldn't want to codify it in a book. Particular objects and devices and particular things, because we're in that phase where if we can teach the process, people will be able to invent and adapt. I still think we're in that phase. At this point, I thought we would, a few years after this, a lot of these basic motifs would be worked out and the materials would be worked out, but that's not been the case at all. And it's the opposite. It seems like it's expanding. So... all right, so this is the most ambitious one.
Okay, yeah. Maybe.
Because it's pressure and position. That's what I was struggling for. So this one is presumably familiar to you.
I'm also noticing now this has got a 1 and a 2, and so I think...
So these are both fabric pressure.
Yeah, and this one's the version that's more maybe the first step that introduces the materials.
Yeah, although it's not completely innocent, the choice there. It's a contrast with the other one, because I was very concerned with how on earth I was going to connect these. These things I knew didn't interface well to conventional electronics. So I was very interested in where the connection points ended up. So here they're on both sides. And here they're accessible on the same side, but you can't run them next to each other easily. So I just point that out by running this the other direction. I mean, I could also run this bottom conductor out this way.
Yeah, or you could cut it I've got to start moving my journal under.
Yeah.
Oh, it's a picture for it. But you could have cut the conductors but then you waste material, where you lose a little bit of the idea that one comes on like this and the other underneath comes out like that.
Right.
But then you lose that piece of material. And you cut 2 of them out.
Yeah, you're also putting next to each other 2 things that fray terribly. The first fabric I used was fraying everywhere, and I thought, well, one of the easiest ways to manage shorts is to just keep these conductors away from each other. So if I was doing this one again, I would probably make both conductors slightly smaller, so they're overshadowed, if you like, by the piezoresistive fabric. And of course, we can manage fray now, but when I was first making this, I thought, I was literally cutting things and bits of copper were flying over. And I thought, no, how are we going to make this fly?
So how have you adhered the copper fabric to this Onyx piezoresistive?
Well, we might have to do some archaeology here. I think most of these pure fabric ones probably don't work very well because I think I just experimented with fabric glue. If it's really well adhered, it must be fabric glue, right? Because by now the acrylic, I didn't have this
You mean
conductive.
the iron-on, or would you have had it in a bottle?
I think I just put a bottle, and I think what I tried to do, but didn't work very well, is run it round the edges.
So that doesn't
interfere with the operation, so there's some interface with that. So this is an interesting opportunity to test whether any of these materials still work. And this was the very early days of Ionics, and most of those materials, the polypyrrole ones, didn't have very good properties. They aged rather quickly. They've fixed that in their newer materials.
Okay. I'm pushing very hard, and it goes down to about 500K. And if I don't push so hard, it goes down to about 800. Oh, it's working.
Yeah. Interesting.
But it doesn't seem to get anything in between it. Oh, yeah, it does. Now I want to check the other one. It's okay.
Yes.
So I'm going to use alligator clips. I think the bottom one I can connect like this, and the top one I will go like this. We have 100, 200K, and I'm squeezing it medium hard, and it goes down to 10K. Yeah. Well, then also now you have so much surface area that I can, if I squeeze it in multiple points, I can go even lower. Nice. I like this design.
Thank you. That company makes very wide, large. So I made a long stick, really long dowel, very large one. And I also did it on the flat. And I showed it to Keith McMillan, who made a product out of the idea called Soft Step. So the enabling, it's one of those things where I had to, this is later in the process, I had to build these other ones to generate the questions for what material I really wanted. And so I started desperately looking for conductive materials, and as soon as I saw the heat shrink, I knew that I wanted it because all these resistive sensors benefit a lot from preloading, right? They benefit a lot from there being some initial pressure before you add pressure. So preloading is a sort of for most sensors, it's helpful not to have them flailing around with no interaction with the world. If you can set them up to have an initial point, they tend to behave better as when you do interact with them. And as soon as I saw the shrink, I thought, it's going to preload this fabric. And that heat shrink's doing a lot for me. It's conductive, it's carrying conductive around a loop, and it's applying the pressure against the piezoresistor. So, and it's flexible. Yeah, so many properties. And I can cut it to length, and I can buy it in different diameters. So, going back to the earlier one, I'm pretty sure this was an attempt. This is all fabric, so
Looks like it has this in between.
Yeah.
So it could be more highly conductive.
Let's see if it actually does anything, because I'm looking at it now and thinking, what was I thinking? And so by all fabric, I kind of mean no traditional electronic bits, even those.
But then I have to say it's interesting that you add the rivets, because what's the need for them if it's fabric and you could sew to it the fabric directly rather than...
Because conductive threads weren't available at this time. There was no rivet.
So you would solder to the rivet.
Yeah. You'll notice every one of these has, well, not this one, I left it ambiguous as to how to connect it, but all these have rivets.
So I'm pushing really hard and it goes down to about 700K. But it's working. It's just the range. I think it's because...
I think we're not, but I don't think we're measuring the sensor at all. I think we might be measuring your fingers.
I don't think my fingers would be in the kilo ohm range.
Oh, wait, it goes down to kilo?
Yeah.
Oh,
but it is...
I'm amazed it still works.
No, maybe, but now it's not going down. Now it's relaxed is
well, the
one.
sun's shining in, we're sweating. I wouldn't be surprised if you could get down to the kilo.
Okay,
If you squeeze
relaxed is 1.3 mega ohm and squeezed is
okay, well,
500K.
Okay, ship it. So now how does it work? What is that intermediate fabric?
This one, I think.
That you're right. I'm remembering now. So what's going on there is that's the very on either side is the very conductive one, and on the inside is the pressure resistive one. And I'm really proud of this one because it doesn't fray. That was what. These are not woven. These are non-woven. And when you think about this, there's no way anything can go wrong with this, and it's sudden. There's no sudden failure mechanism in this one.
So then maybe we can go to this because it's using that same in-between fabric? Or conceptually is this one?
So, well, this is an interesting hybrid because I'm not inventing these from scratch. I'd already studied, for example, well, piezoresistivity has been exploited for over 100 years. The most recent commercial enthusiast is Interlink, that makes all these devices using printed. This is the XYZ sensor taken apart with the piezoresistive. It's piezoresistive and silver. So there's one sheet that's folded, and it's got horizontal. It's on this side. It's got this oriented that way, forming a divider between the resistive material that way, and then on the other one, it's on the other axis. And then when you press together, you can read out X, Y. But the reason I'm showing you this is it's got piezoresistivity and silver. So this is what's going on here. I drew silver onto some plastic, and in the classic interdigitated way, with a bit of a swirl, and added the...
So you have two coils going up that are interdigitated, interswirled. And then you have this same non-woven carbon-doped fabric on the back. Okay. But what I was thinking about this one is nice is that it's all the same fabric. It's all the same non-woven base material. It's been doped differently, and but you end up with a thing that's, I don't know, it doesn't, even though it's layered. I mean, as a non-woven thing, I wonder if you could even felt it together in these layers and achieve this.
Well, certainly, you can imagine buying sheets of that pre-made that way.
That's why I was wondering now, in contrast to that, how this is solved. But this is possibly different.
I have no idea what that is. I've got to take a look at it again. What was I thinking? Oh, it seems like I found a shield fabric from somebody. Yeah, that looks like the layered tape, don't you think?
It looks to me like the ripstop, silverized ripstop, and then you can tell it's got glue around the bottom because it's seeping out here too. But yeah, you can see you put the glue just around the edges. In the middle,
right.
It looks like this.
So hopefully that works. Because silver would stay good, and that fabric might have retained some.
Okay, and here we have Okay, is that to reinforce the rivets going through a little piece of that here?
Yeah.
It's just because...
Yeah, I found it was too thin. The first time I punched it, it just was too loose.
Do you still have the tool that you do the rivets with?
Well, not probably the very same one I did that rivet with. But yes, I have riveting tools that work with.
Okay, there's like infinite resistance when it's relaxed, and when I push really, really hard, nothing happens. I wonder if we do it just on a piece of this. Infinite resistance, and under pressure, nothing happens.
Yeah, this happened to me with a few of the early fabrics from e-Onyx, is that they completely lost their
So that's why this one wasn't working.
Oh, it could be. Yeah, we didn't test that material, but
Yeah.
we really have no resistance anywhere along this.
Oh yeah, we didn't even, but I'm guessing not.
Wow.
Yeah.
Yeah.
And this one though, that you mentioned, probably got some coating on top, right?
It's actually all happening on the inside. That's where it's all. Let's just unfold it. There you go.
30K.
Yeah. Those are the sorts of numbers. Yeah. So we've done that one. So the thing here is, again, I was concerned about fray and just very happy about this resistive non-woven because it didn't fray. But I wanted to sort of show that there's this whole question of managing very conductive and not so conductive.
This whole part, it feels like you could have cut it off just here.
I could. What I had in mind to do
You could do multiple ones.
was multiple ones, yes, exactly. But I think I got bored with it. It seemed obvious to me that once you'd got one of these going, you can extend it.
No, I think you do at least one more to make that demonstration.
Yeah, well, what happens, I got all excited about, maybe I can make the Holy Grail one is this one, right, where you've got pressure and position in the one sensor.
So I can see copper ripstop on the very top with a little tab coming out here. So there was obviously 3 legs coming off. Then I can kind of see some toile, what's it called? Tool, like spacer fabric. Then the middle pin is going to some e-Onyx and the other side as well. So here, instead of having like these two direct sandwich,
right,
you have a spacer, so you have a complete off position, which means now in order to get, you said it can do pressure and position. So the position it's getting by reading just between, let's say, well, yeah, it must be the middle and the copper. So it's like but then why is okay, no, because the spacer is between the 2 black layers. So then it must be reading between the 2 black layers to get the position. And then to get the pressure, it's reading between the top copper and the bottom black.
Sounds good.
And if you had this set up with a piece of magnetic material in the back, some steel fabric and a little magnet on top, you could have a
slider.
Yeah, you could have a slider.
A slide pot where you can sense whether someone's touched it, which is actually how slide pots on expensive mixing consoles work. Because they're motorized and they want to know whether you're about to change the value.
So let's try that now. So we can only do one thing at a time. Let's just try pressure.
I think that one's the position. I'm so confused now.
No, this is pressure. Position is I think both would actually work for position.
Well, I don't get much of a change. Let's get the magnet out of the picture. 13 there, and then...
My sense a bit would be, though, that you would want to have the spacer between the copper and the piezoresistive, because then you don't... Because the spacers between the two black fabrics, and they're pressure sensitive as well, so then you don't have a clear connection when you touch. So also how hard you're pressing is also interfering with where along it you're pressing.
I think that disturbed me a lot, except that I knew they had very good control over the amount of resistivity. So I think the idea was that the center one was very conductive.
Oh, so it's two different kinds of...
Yeah.
But if the center one's very conductive, then it's not going to change resistance so much when you pressure it, and you'd want to have a bigger pressure range. It would make sense if the back one was very conductive. Yeah, actually, it would make sense that the top and the bottom are copper, and only the middle one needs to be piezoresistive, and then the spacer can go either side of it.
Yes, and because of the fray problem, you're right. The bottom one is the very conductive. Does it look like the thick stuff? It's funny, the middle looks like the thick stuff. Looks like they're really conductive. We should test whether they have the right properties.
We can just see, like, over about 2 centimeters, we have 1.5 K.
That's pretty conductive.
Yeah.
So that's still to be working. It's impressive.
It looks like there's even some of that grey material used here also as another spacer. So, and you can kind of see it looks like there's a frame going.
Yeah.
You can feel it, I think, or maybe... Oh no, maybe it's just the glue. You can't feel a frame.
Yeah, so you've got it. It turns out that this one's the pressure one, using the grey fabric as the pressure sensor in the middle, and then this is just the classic position with wiper floating over the top.
You have 4 layers.
Yeah.
But you could probably do it in 3.
I could now, You could do it now in 3, but at that point I was just wanting to know if it was possible at all. Because to my knowledge at that time no one had done it.
Yeah, and I think what I find amazing here is that this spacer fabric, like, you just have to find the right thickness and size of hole, and then it's amazing how it actually does not allow contact, and then you just have to stroke it. You don't have to push to make that connection. I saw that the first time
it took me a long time to find a good name for that fabric. I really think this word porous is helpful though, because porous you usually think of as liquids getting through holes. That's how some filter systems for water, you put an array of small holes and the water gets through the holes, but not the big molecules you don't like. So, but it's unusual to think of porous materials as allowing solids to move through a hole, but that's really what I'm excited about. And it's an interesting twist, because I was slow to learning at this point the textile universe, but textiles, these tools, these nettings, they're definitely, their porosity to light is really what's going on there. It's the way that they're often used to create shadows and interesting changes to the light passing through the holes. So, and textile being probably the oldest important technology for people, it also evokes the nets that had to do with catching fish. So I view this as a very very old ideas being put together. That's I don't know all the history of tulle and netting. It certainly was the thing that struck me the most when seeing the Mona Lisa in person, because all the reproductions of it don't show this, but the lace work, the the ability those painters had to paint that delicate kind of array. It was a way of showing off this kind of virtuosity for those painters to have the portraits have people wearing these incredibly fine veils. I don't know what they used for paintbrushes, probably pins. So yeah. And what's odd about this period for me is that it still seems like I can get leverage out of the same small number of things. Like there's still Keith McMillan has picked up on these materials and done some products with them, and he has a kind of joystick that just combines multiple pressure sensors, pretty much following again the same strategy of Interlink, looking at how Interlink solved this problem with the joystick. And that's 4 separate piezo-resistive sensors with the interdigitation. So here's my interdigitation. So
and this structure, I feel weaving or maybe even lace making, like classic textile techniques that would allow you to work with 2 different colors where they do not have to touch.
Yes, it turns out when I look at this, I see some math I learnt in school with space-filling curves, Sierpinski curves and Hilbert curves, which are interesting. When I was learning them, it was considered pure math. It didn't have much of an application, but it was an interesting question about how to get as many continuous lines to fill a space, unbroken lines to fill a space. Because you get this funny thing happening where seems like you can keep getting the length of the line to go up and up and up without limit and fill the curve. Turns out that these structures are used in electronics and have been for quite a while to make capacitors on chips. And they're used to design radio antennae for cell phones.
So here, this one goes around to here and fills in this space. This one goes and fills this space. And then there's a central one that kind of infiltrates all of them.
Yep, infiltrate's a great word for that. And then there's because at first it feels like, it looks to me like, okay, so you have A, B, C, D, E, and you have A and B, A and C, but actually A is going everywhere. Yes.
Yeah, it's really interlinked, interdigitized. And then these are actually the directions, left, right. It's not the corner, but the space, which also makes sense. Yeah,
because what their patent is bragging about is that you get some smoothing just because of the physical arrangement. You don't have to combine the 2 values in software. You already have a kind of smoothing going on in the physical arrangement. And I just like, this obsession with trying to line up a neat row of connections. I like seeing how that mead is expressed in these kind of broken symmetry, because this one has to run all the way around, and then there's another one that has to run all the way around to get there. So you see it's not quite symmetric. It sort of reveals the tension between the symmetry that's natural in what you're trying to measure evenly, and another kind of regularity you want, which is a linear. So there's a circular spatial regularity in tension with a linear one you want to line up the connections.
But I guess what's also interesting is, why do they make it like one long space-filling curve versus having the center be something that, I don't know, branches out like... this, and then you have, I don't know, more like antennas, and then you have A filling in like this, B filling here. Sorry, that would be B, C, and A is the comment. I wonder why it's one long line, because there's no reason for that. I don't even know if it's exactly one long line, but it's definitely seems to me possible that it could be.
Well, this gets into the theory of space-filling curves. There's a kind of...
I guess this allows you for the A to end up down here, instead of coming out like that.
Yeah. Also, there are stylistic choices, like there are different space-filling curves, and it has to do with when they turn corners and how often you want them to turn corners. So you can take that design and make it more interdigitated and interleaved by turning everywhere you see a line, another line.
Oh, you do have... Sorry,
it's turning corners.
It's basically like this, except it goes once longer on this side, once longer on that side, once longer on this side. I think that's what it looks like. And then the center point. So this is actually the one coming out from the outside, so B, and then A kind of goes back and forth between, because you've got the same going on here.
Yeah, these things are fun. There's so many questions. Like there's no reason why it has to be these filled with right angles as well.
Mm-hmm. That's true. That's also interesting. Why not? Since this is
circular, why not reach for a more circular thing? Now you see this in maze design. Right? There's some beautiful maze designs that are circular. And maze designs have something in common, because you wander around and then there are breaks in the bushes, right, that you have to decide whether to pass through to another track. Mm-hmm. And the challenge of this design is as much to make sure that there are breaks everywhere there need to be, so that the things are not touching each other. There's another way to think of this, is think about the negative space, is that you could fill all these things with lines and then decide where to break them to make sure you're kind of collecting all the conductors that belong to A and all the conductors that belong, segments that belong to this. Another way of thinking about it. That's in a way, one way of doing maze design. Now, fortunately, my teacher, when I was in middle school, was into sharing recreational math with students. And so we were noodling around with maze designs and so on. So when I saw all this, it had this very familiar thing to me. Not that I understood without some study what was going on there, but it had a familiarity. Well, these pens are clean. So orange peel is probably piezo resistive.